This is a Bosch Rexroth ctrlX Core X3, and this is an Invertek Optidrive P2 inverter drive. In this video, I'm going to show you how to control the P2 over EtherCAT from a PLC program running on the X3. Hello, I'm Simon from the Inverter Drive Supermarket. In the previous videos, I showed you how to connect to and control a Bosch Rexroth EFC5610 over EtherCAT using a ctrlX Core X3. But what if you need to control a third-party drive from the X3? To demonstrate the process, I'm using an Invertek Optidrive P2, and over the next 20 minutes I'll show you how to control it from the PLC and operate it alongside the EFC5610 all over EtherCAT. If this kind of practical industrial automation content is useful to you, consider subscribing. It really helps the channel. I've already installed the optional EtherCAT communications module in the P2. Now I simply need to enable advanced parameters by setting parameter P1-14 to 101, and then set the drive to field bus control mode by setting parameter P1-12 to 4. From an I/O perspective, I've disabled STO using the yellow and black wires as you can see here, and I've linked the enable with the red wire. The enable is essential, without it the P2 won't run the motor. And that's the P2 configured. I can connect it to the EtherCAT network using a shielded RJ45 cable, and I'm going to use the second port on the multi-Ethernet card we fitted to the EFC for this. In the earlier videos, the EFC was detected automatically by ctrlX I/O engineering because its device description is included by default. For the Invertek Optidrive P2, that isn't the case, so we first need to add its EtherCAT device description to the I/O engineering repository before scanning. Invertek provide these files on their website, so let's download the correct one for the EtherCAT module we're using. Visit invertekdrives.com, click Support, then find Quick Links and click Software and User Guides. Then P2 Assist, Software Downloads, and scroll down until you see the Configuration File section. Click to download for the EtherCAT module. The zip file includes a PDF user guide which we'll use later to understand and map the data, and an XML file which is the slave interface identification. Now we have the files we need, we can add them to the X3. I'm going to start ctrlX I/O engineering and open the demo I/O project we created in the EtherCAT video. Click Tools, then Device Repository. Click Install. Then select the XML file from the download and click Open. As you can see, Invertek Optidrive has been installed to the device repository. Now we can scan for it. Click Close. Right-click the EtherCAT master node in the project tree on the left and select Scan for Devices. Log in using your usual X3 credentials if prompted. An Invertek Optidrive has been found. Perfect. Click on the Insert All Newly Scanned Devices button in the middle to add the P2 to the project. Then click OK. Now we can see it in the project tree, double-click to open it and select the I/O Variables tab. If we switch between this and the EFC, you can see that the data structure is different. The Invertek device profile is structured as an array. Both the control and status data contain 4 words each. We'll need to ensure we handle this correctly in our PLC program. We'll do this shortly. Before we're finished with I/O engineering, we need to transfer the changes to the X3. To do this, right-click EtherCAT Master in the project tree and select Download. Log in using your usual X3 credentials if prompted. Finally, save the project so it's transferred to the X3 too. We're done with I/O engineering, so can close it. Now we've added the Invertek Optidrive P2 to the EtherCAT network, we also need to add its real-time data to the PLC project. To do this, right-click EtherCAT Master, Instances, EtherCAT Master, select Real-Time Data, then selectively from ctrlX Core. Enter the username and password for the X3 if prompted. Expand the new Invertek Optidrive node. The 2 data arrays we saw earlier are visible, one for status and another for control. I'm going to select both and apply the changes using the button in the middle. The real-time data is now available to the PLC program, but before we can use it, we need to understand what data it contains. Data is exchanged over EtherCAT according to a device profile. As we've seen, the Invertek P2 uses two data arrays: the input data array, which the drive receives, and an output data array, which the drive transmits. Both arrays contain 4 16-bit words. The input data array contains the control word, the frequency set point, and 2 user-defined words. This is how the data from the control word is structured. We can run and stop the drive with bit 0, perform a fast stop with bit 1, reset a fault using bit 2, and coast to stop with bit 3. The 16-bit word representing frequency set point is simply a number. The user guide states that it is to 1 decimal place, so we'll need to divide it by 10 to get the value in hertz. The output data array contains the status word, output frequency, and 2 user-defined words. The status word consists of 5 bits and 1 byte. The bits can be used to read running or stopped state, indicate a trip, flag maintenance requirements, and so on. Bits 8 to 15, also known as the high byte, will return the last or current error code as a number. Like the frequency set point, output frequency is also a 16-bit word representing a numeric value. In this case, it represents the live output frequency of the P2. So now we understand the data structure, we can add variables to the PLC program for the control word, frequency set point, status word, and output frequency. We can define structs for the control and status words as they each contain multiple values. I've already written these, so we'll simply copy and paste them in. Right-click EFC and select Add Object and DUT. Name it UDT_P2 control word. Paste in the definition from the user guide. Add another data unit type, name it UDT P2 status word, and paste in the definition. Now we've added the structs, we need to create variables for them. Select the PRG EFC01 tab and add the following variables after our output freq. The first is STP2 control word, which will be the variable for our control word struct. Next, add STP2 status word, which will be the variable for our status word struct. Then a P2 status data, which will hold the raw status data array from the P2. And finally, a P2 control data, which will hold the raw control data array from the P2. Both arrays consist of 4 unsigned 16-bit integers, hence 0 to 3 of uint. In PLC terms, a 16-bit value is 1 word, so each array contains 4 words of data. However, we'll only be using the first 2 words from each in this example. Now the variables are defined, we need to map them to the I/O so they contain real data. To do this, first double-click on the Invertek Optidrive node in Data Layer Real-Time. You can see the 2 real-time data channels we scanned for and added earlier. However, there are no variables assigned to them. This means that the PLC is reading the real-time data but has nowhere to put it. To fix this, we need to map each channel to a variable. Double-click the variable for the status data channel and click the ellipsis button. Expand Application, EFC, and PRG EFC01 to see the variables in the PLC program. Select a P2 status data and click OK. Press Enter. Repeat the process for the control data channel, mapping it to a P2 control data. Now the variables are mapped, we can move on to the PLC program. Select the PRG EFC01 tab, right-click on the last rung and select Insert Network below. This adds a new rung to the ladder. Right-click on the new rung and select Insert Empty Box with Enable Output. This adds an empty function block with Enable and Enable Output. Click the question marks inside the box, then click the ellipsis button. In Input Assistant, select the Text Search tab and search for Word to Bool. Double-click CXA Utilities IL Word to Bool in the results to select it. Click Away to update the box. Change the name to IL_Word to Bool_P2 and click OK. This creates the required variable for the function block we just added. Delete the contact, we don't need it. The input should be set to a P2 status data with 0 in square brackets, as the status word is the first word in the status data array. Then bind the outputs to each of the bits in the P2 status word struct variable. They are bit 0, running, bit 1, error, bit 2, hand control, bit 3, inhibit, bit 4, maintenance due, and bit 5, bit 6, and bit 7 are all reserved. Just like the EFC5610, bits 8 to 15 represent the error code, so we can handle it in the same way. Right-click and insert another empty box with Enable Output. Click the question marks inside the box, then click the ellipsis button. In Input Assistant, ensure the Text Search tab is selected and search for high byte. Double-click CXA Utilities IL high byte in the results to select it. Click Away to update the box. Set the input to P2 status data with 0 in square brackets as the error code is part of the status word. Assign the output to P2 status word by bit 8 to 15 error code. And that's the status word done. Add a new rung to the ladder. Then add a function block with Enable Output. Name it word_to_real. Delete the contact, it's not required. The input should be set to P2 status data with 1 in square brackets, as the output frequency is the second word in the status data array. Name the output P2 Output Freq. In Input Assistant, ensure the type is real and the initialization value is 0.0. The user manual states that the output frequency resolution is 0.1, so 23.4 Hz would appear as 234. This means we need to divide the raw output frequency value by 10 to read the actual value in Hz. We can do this using the built-in divide function block. Add another function block with Enable Output to the current rung and click the ellipsis button. Select the Text Search tab and search for div. Double-click div in the results to select it. And click Away to update the function block. Set the inputs to P2 Output Freq and 10. Set the output to P2 Output Freq as well. And that's the output frequency done. Add a new rung to the ladder. Then add a function block with Enable Output. Open Input Assistant, ensure the Text Search tab is selected and search for bool to word. Double-click CXA Utilities IL bool to word in the results to select it. Click Away to update the function block. Delete the contact, we don't need it. The output should be set to P2 control data with 0 in square brackets, as the control word is the first word in the control data array. Then bind the inputs to each of the bits in the P2 control word struct variable. They are bit 0, run command, bit 1, stop ramp 2, bit 2, fault reset, and bit 3, coast to stop. The remaining bits 4 to 15 are not used, so they can be set to 0. That's the status word sorted. Add a new rung to the ladder. Then add a function block with Enable Output. Name the function block real_to_word. Delete the contact on the enable. Assign the output to P2 control data with 1 in square brackets, as the frequency command is the second word in the control data array. Assign the input to a new variable called P2 Freq command and set the type to real and initialization to 0.0 in auto-declare. To correct the resolution, change P2 Freq command to P2 Freq command multiplied by real #10.0. That's all the function blocks added. We now need a couple of rungs to specify when the P2 should run and at what speed. For this demonstration, the P2 will run when the EFC output frequency is greater than or equal to 25 Hz. If the output frequency is less than 25 Hz, the P2 will stop. So add a new rung to the ladder, then add a function block with Enable Output. Delete the contact, we don't need it. Open Input Assistant, ensure the text search tab is selected and search for GE. GE is the built-in greater than or equal to function. Double-click GE in the results to select it. Click away to update the function block. The input should be set to R output freq, which is the variable holding the output frequency of the EFC, and 25, which is our threshold. The output should be set to P2 control word bbit0 run command, which instructs the P2 to run. This will make the P2 run and stop. Now we need to specify the speed. Add a new rung to the ladder. Then add a function block with enable output. Open Input Assistant, ensure the text search tab is selected and search for the move function. You can think of move as saying, make this value the same as that value. So double-click move in the results to select it. Click away to update the function block. We do need the contact this time. Set the value to P2 control word bbit0 run command. This means that the frequency setting only applies when the P2 has been instructed to run. The input should be set to rfreq command, which is the variable holding the frequency set point of the EFC, and the output should be set to P2 freq command, so the EFC set point is copied to the P2. So now the P2 will run with the EFC in perfect EtherCAT harmony, provided the EFC is running at 25 Hz or more. Beautiful. Now the changes are complete, we need to transfer them from this laptop to the X3. To update the X3, click Online, then log in. Enter your usual X3 credentials and click OK. Accept the certificate if prompted. The application has changed, so click OK. You'll be notified if a full download is required instead of an online change, but that's OK too. Once the X3 has been updated, right-click Application and click Start. Now I'll select the Visualization tab so we can try it out. I'm using the same Bosch Rexroth EFC5610 and X3 demo rigs that we've used throughout the previous videos. The only difference this time is I've added a second motor which is connected to the Invertek P2. To test everything, the first step is to enable bit 7, which tells the EFC that it should accept an external command. Next, I'll set the speed reference to around 20 Hz and start the system. You can see that the motor connected to the EFC accelerates up to the required speed whilst the P2 motor remains stopped, exactly as expected. Now if I increase the frequency reference to 40 Hz, the EFC motor speeds up and the P2 motor starts. Both motors accelerate smoothly up to 40 Hz. If I then reduce the speed reference to 30 Hz, both motors decelerate together. And finally, when I drop the speed below 25 Hz, the EFC motor slows down as normal, whilst the P2 motor stops. So the logic is working exactly as intended. Both motors are responding correctly, with the Bosch Rexroth and Invertek drives operating together seamlessly over EtherCAT. That's it for this video. Thanks for watching. In the next one, we'll enable and configure secure remote access so the X3 and EFC can be accessed safely from anywhere in the world. If you found this video useful, please give it a thumbs up and consider subscribing so you're the first to know when we release new content. See you next time. This video is for educational purposes only. Always follow official manufacturer documentation and safety instructions.